Okay, let's get started. Happy Monday, everyone. Let's talk about the schedule a little bit. We are working our way through our section on cognitive psychology, the inner workings of your skull. Obviously, we don't have a lot of time in this class to talk about that, so we are doing an extreme crash course in cognitive psychology. We're working our way through 11, 12, 13, and 14. We're starting with relatively objective aspects of cognition, which is I push against the world, and my mental model makes a prediction about how the world is going to push back. When the world actually does push back, I compare the actual sensory repercussions of my actions with what the mental model predicted, and if they don't match up, then either I'm frustrated or I'm interested because there's something new here that I haven't seen before in an app or a game or what have you, right? So hopefully, as you're designing your HCI systems, like the ASL system for this class, you're thinking about that. What is your user expecting to see at the next frame of the animation, or when the timer that they see in the top right runs down to 0? Okay, that's mental models. We finished that last time. We're going to talk today about memory, attention, and perception. We all know that we have these three things, but how these three things actually work in the brain is a little less clear than mental models or forward models in the brain. We're then going to get into Gestalt Perception. Hopefully, we might start that today. We'll see how things go. In the frame of reference problem, and we'll end with the most subjective aspect of cognition, which is affect or emotion. The reading for today was just a moment ago, the reading for Friday, so you may already have done this. This is a chapter from a book I co-authored a few years ago with Rolf Pfeiffer called How the Body Shapes the Way We Think, and chapter 10 is about memory. Okay, so if you've already read it, you're good. Otherwise, that's the reading for today. Deliverable 8 is due next Wednesday, and we'll talk about deliverable 9 next Wednesday. Any questions about deliverable 8? You're building in your database, and you're collecting your username, which you're doing at the terminal before you start up your infinite loop of visualizations. Pretty straightforward. All right, so let's get to memory, attention, and perception. These are obviously three aspects of cognition which are important when you're designing your HCI system, right? Are you aware of what you're forcing your users to remember or recognize? Is it clear to your system what the user is attending to or what aspect of your system they're focused on at the current time? And are you providing visualizations so that they can perceive the pattern in the colored pixels that you're trying to communicate to them? So we're going to walk our way through memory, attention, and perception today in this lecture, and those aspects of those three that relate to HCI, right? So when we talk about memory, it's either a noun or it's a verb, right? A memory of your grandmother or the process of remembering. Usually this is broken down into recall and recognition. You remember a few weeks ago we were playing the photograph game where I showed you 2 frames of a cartoon and you had to figure out what's different between these 2 pictures. You saccade to one image and then your eyes move to the other image and you need to recall what was there at that point in the cartoon and compare it mentally with what's there in the new cartoon when you look at it, right? Recall is a little bit trickier. Recognition is a lot easier, right? You recognize that something is changing or different. Okay, we're going to talk about that. And of course, we can break memory down into short-term and long-term memory. Attention is your ability to focus your mental resources on things that are happening outside, hopefully this lecture, or things that are happening internal, and how exactly does that work? How do you allocate mental effort to things going on around you or in you? Internal may be daydreaming, right? I'm actually updating my mental models, or I'm thinking about what happened yesterday or an hour ago, and I'm using my mental models to think about what's going to happen this afternoon or tomorrow or next week or next year. Okay. Perception is very different from sensation, and we're going to come back to this later in the course. If your eyes are open, you can't help photons falling on your eyes and stimulating the earlier parts of your visual system. That just happens as long as your eyes are open. It's a relatively passive process. But perceiving is an active process, right? We've talked about saccades quite a bit. You're looking at one part of the Necker cube and you're trying to figure out what this thing is. You make a prediction, your eyes saccade move to a different part of the Necker cube, and when your eyes arrive at that point, you compare what you see with what you predicted to see, right? That's perception. Someone clicks on a button on your screen and they make a prediction about what they're going to see or hear at the next time instance. Usually you're using these perceptions to prove or disprove your mental models, and again, your body is moving to do this. With passive sight, it's not that obvious, but that is what you're doing, right? You're actively saccading around and moving your eyes to attend to different parts of the screen, for example, or you're moving your head to clarify occlusions. You're acting on the world. Okay, so we're going to talk about memory, attention, and perception. We all know we have it. It's obvious, but it's not so obvious really what it is. So I want to start with a warning, and this is a warning that has existed in artificial intelligence for the last 60 years, which is thinking about thinking is misleading. If I show you an image with a person in it, you can probably recognize that person almost instantaneously if it's a celebrity or someone that's relatively familiar. It's easy to recognize people in images. It took 40 years, or 50 years, depending on how you're counting, to get a computer to do it. Visual facial recognition is trivial. We do it all the time. In the 60s, when they started on this, they thought it'll take us about 3 weeks to get this problem nailed down. It took 40 or 50 years, depending on how you count. Thinking about thinking is misleading. We remember things, we attend to things, we perceive things effortlessly. Doesn't necessarily mean those are easy processes because we're not sure how those processes work. So just for fun, here's another aspect of cognition which we will not come back to, but is obviously important: free will, right? You decide to look at me or to look at the screen or to take some notes or to look at a YouTube video on your laptop. You chose, right? You have free will. It seems obvious. It's a very interesting and controversial experiment led by Libet and colleagues, a psychologist, back in the 80s that militated against this view. Has anyone seen the Libet experiment before? No? Okay. You should enjoy this. All right. Libet and his colleagues invited a bunch of human subjects into the lab, and they were instrumented with EEG and EMG. So an EEG band is something you can wear on your head, and it's able to pick up electrical activity at the surface of your brain. It's not so good at getting signals at the interior of the brain. EEG's come a long way since the 80s. We'll see EEG again right at the end of the course when we talk about brain-computer interaction. So EEG records brain activity. EMG, electromyography, records muscle activity. So they put an EMG strap on each of the patient's fingers, and the subjects were then asked to look at a clock with a moving second hand, and there was a red light on the second hand. The subjects were asked to decide at some arbitrary point to move their finger and then move their finger. They were then supposed to report to the investigators what was the exact time at which you decided to move your finger. So far, so good? Okay, so the investigators then looked at the data after doing this with a large number of subjects and saw that at about 200 milliseconds after people had decided to move their fingers moved, which was good news because that's about how long it takes signals to get from the brain to your finger, 0.2 of a second. So it seemed most people were obeying the instructions. They were deciding to move their finger, and then they moved their finger. For each of the subjects, there was a particular brain activity pattern that showed up 200 milliseconds before that subject's fingers moved. So whenever, and I'm sorry, I forgot to mention, each subject did this multiple times. So whenever they actually recorded the finger moving with EMG, that particular pattern appeared 200 milliseconds earlier. So whatever that pattern was, it was somehow associated with the person choosing to move their finger. That particular EEG pattern was different for different subjects. All our brain activity is very different, right, like your fingerprints. But there definitely was this consistent brain activity pattern that showed up 200 milliseconds before the movement, and that particular EEG pattern seemed to match up pretty much exactly with the moment in time in which the subjects reported that they had decided to move their finger. So far, so good. You may be able to see where this is going. It turns out that 300 milliseconds before that, there was another pattern that also always showed up whenever the subject moved their finger. So they would always see this particular EEG pattern, then this pattern, then this pattern. And again, these patterns were different in different subjects, but they were consistent within the same subject. So the subject thought, or at least reported, that they had moved their finger at this point in time, but it seemed that they had actually, quote unquote, made up their mind 300 milliseconds earlier, but they weren't aware of it. Does this worry you at all? Kai, you're shaking your head no. Why not?
I mean, I feel like I've come to the same conclusion, like, another way.
Okay.
Like, why does anyone decide to do anything in general? Like, because they like it or because it will help them in some way? So why do we like that, or why do we think it will help us? If you keep following the logic, it just kind of continues. Also, it doesn't seem like it's not free. We still have this kind of illusion of control.
We have this illusion of control. Whatever we did probably served our interests in some way. In this case, the decision to move the finger seemed to be subconscious, right? The subjects were not aware that they had decided at this time, to move their finger. But if they're not conscious of it, how did they decide? If you ask somebody, they would say, I decided at this time to move my finger. But it wasn't really the conscious I, it was the unconscious part of their brain that decided. Okay, so I am not here to try and dampen your Monday morning that you don't have free will, but this is one of many, many examples that shows that our feelings about our mental processes may not be as obvious as we think they are. Yes?
Would that happen in, like, reflexes?
Reflexes are different, right? That's not free will. You can't help drawing your hand back from the stove if you touch it, right? It just happens. This is something where it's clearly set up to make you feel, to give you the freedom to decide when to do something.
We're all pre-programmed then.
Perhaps. I don't know. This is just the data that we have from the Libet experiment. Okay, so just remember as we continue, thinking about thinking is misleading. Yes?
I'm just curious as to what their definition of free will would be.
Exactly, right? I don't think they actually give one. They're very careful to just say, this was the experiment, this was the data we saw. What free will means to one person might be very different from what it means to someone else. But freedom is in there somewhere, right? And if your subconscious is the one that's making decisions for you, for your conscious self, is this still free will? Okay. A lot has been written by Libet and about Libet's experiment, so if you're interested in this, go have a look in the psychology literature. Okay, let's carry on with memory, attention, and perception. Again, we try and tease apart all these aspects of cognition. Creating mental models, perceiving things, freely choosing to do something. But of course, in the brain, they're probably not separate sections. There isn't the free will section and the mental model making section and so on, right? These are very highly interdependent processes, and we try and tease them apart and give them separate names so that we can try and study them and get a better handle on what they actually are. Right? Of course, these particular three are highly interdependent. Your memory is a result of what you perceive. If you don't perceive something, you don't remember it. Changes in attention, the moment you saccade or look at something else or listen to something else, changes your perception and again what you're going to remember. Memories shape our perceptions. What other interdependencies exist between these three things? How does your perception affect memory? How does your attention affect perception? We talked about attention being something, a currency, something that you can expend. If you're kind of paying attention to something, you're going to partly perceive it and probably have a harder time recalling it later, right? The less attention, the less perception, the less memory for later. Okay, so we're going to talk about these things as three separate things, but of course they're not really separate things. Okay, let's start with memory. And again, because we're in the psychology part of this class, we're going to do a lot of optical illusions and other little games here. So we're going to play a memory game now. If you don't have a piece of paper in front of you, please pull one out. And here's what we're going to do. On the next slide, I'm going to flash up a whole bunch of numbers. I'm going to show you those numbers for about 20 seconds. Let's say exactly 20 seconds. Do not write anything down while you're looking at the numbers. Just remember as many of the numbers as you can. After the 20 seconds of you trying to remember the numbers, I'm going to flip forward to a blank slide. And I want you to immediately write down as many numbers as you can remember. All right? Okay. Here we go. 5, 4, 3, 2, 1. Ten seconds. Okay, write down as many numbers as you can remember. We good? Okay. How many did you get right? How many got one number? Hands up if you got one number. Keep your hands up if you got two numbers, 3 numbers, 4 numbers, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 13 numbers. Pretty good. Much better than last year, actually. Well done. Okay, here we go. We're going to play exactly the same game. I'm going to give you 20 seconds again. Look at the numbers. Remember as many of the numbers as possible. I'll give you 20 seconds, and then we'll see how many you can recall. 3, 2, 1. Ten seconds. All right, are we good? Okay. How many did you get right? How many got at least one digit correct? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, a little bit better than last time, which is what I was hoping to see. Why? Chunking, right? So I've grouped numbers together for you, which helps, right? Memorizing a flat, formless list of numbers or anything is very difficult. What else may have helped you here aside from just chunking?
You know area codes.
You know area.
Associated with certain numbers.
Okay, perhaps. Does anybody recognize any of these area codes here, unfortunately? Okay.
It's like a certain cadence, which I use to say phone numbers, and that can help.
Yes. So for those of you that are old enough to actually remember having to remember phone numbers, there's that cadence, right? Exactly. 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, right? There's something familiar about this particular pattern, which has been around for a while. Maybe this effect will start to fade now that we no longer need to remember telephone numbers. So chunking helps, but also this issue of context, right? Your brain is wired up to remember things that are organized in particular ways, right? Okay. You might also have done slightly worse on the second round. Why? What's working against you the second time around?
The numbers from the previous round?
Exactly, right? So short-term memory is there. It's hard to erase, right? It's there. It's going to get in the way. That's called interference. So that's another aspect of memory that's going on here. If we played this 17 times, how might you do? Why might you do worse on the 17th time compared to the 10th or 5th time?
People from other countries memorize numbers differently too, so that could be.
That might make a difference as well, right? So not everyone is familiar with this particular pattern.
Like
Right?
Europe, they do it by twos.
Absolutely, right? There's a different cadence. Why might you start doing worse on the 17th time? You're tired, right? You're all either you have midterms or you've had midterms, right? Attention, in order to remember, you need to attend consciously to these numbers, right? It is an effortful endeavor. Probably not during the semester, but if you're looking for any holiday break reading, I highly recommend Thinking Fast and Slow. It's written by a Nobel laureate in economics who talks about these two different modes of thinking, slow and fast thinking. I was forcing you here to work on slow thinking, concentrating on something, trying to remember it. As you all know, because you do a lot of studying, it gets tiring and it becomes harder to attend to and draw patterns out of information after a while. Okay. What else can help? So again, you want your user to learn and remember your system relatively easily with little effort. How can you make their lives easier? Your users are going to have to remember what the signs are for the 10 digits and remember how to call up the lesson for digit 3 because they want to brush up on the digit 3. There's a lot they're going to need to remember or recognize. How can you make that easier for them? There's a lot of material in this course that you need to remember. So I've tried to organize things hierarchically for you. So there are 3 levels here. There are the 5 overall themes. For each of those themes, there's a set of slides. In each slide deck, there's an individual slide, right? I've tried to organize things hierarchically. So if you want to go back and brush up on a particular concept, it should be relatively easy for you to remember where that concept is in all of the lecture notes. Okay, so organizing things hierarchically helps to remember. Okay, let's talk about working memory and long-term memory. Short-term memory is pretty limited, right? No one got more than 13 digits. You definitely had enough time to read more than 13 digits. There are all these arguments in psychology about how much you actually can remember. Doesn't matter for our purposes. What matters is it's very little, right? Okay. Long-term memory, on the other hand, as long as you can turn short-term memory into long-term memory, seems to be about unlimited or infinite if you like. The hard part is bringing it back again, right? There was a famous experiment a professor did where he tracked down some of his students 30 years later, called them on the phone and asked them questions from the course. And a lot of them, with some prompting from him, could remember that material. They probably hadn't thought about it in 30 years, but it's in there somewhere. As far as we can tell, you have about 10 to the 14 synapses in your brain. And most humans these days live for between 10 to the 9 and 10 to the 10 seconds. So if synapses helped to draw information out of a single second of your waking life, you have more than enough synapses to remember every single second of your life. You may not feel that you do, but it's probably in there somewhere. The hard part is calling it back, right? Same thing with studying. You see a question on the midterm, you know what the answer is. You cannot pull it out, right? Okay, so how do we help to translate short-term memory into long-term memory? This could be a little tutorial on study habits. You probably have your own suggestions. Internal rehearsal helps, right? The worst thing you can do is just kind of sit there and gloss over the slides. Turning short-term into long-term memory is, in essence, an active process, right? So if you're reading something, you're saying it back to yourself in an internal voice. You can externally rehearse things. If you write equations in math class, often you can remember the movements of your hands, and that will call up the equations for you. I don't remember the combination from my lock in high school, but if I were to be put in front of that lock, I could probably open it just from muscle memory, right? It's in some other part of the brain, some other pathway that has to do with movement. Okay. The more of your sensor modalities you can bring to bear on a problem, the better it is at remembering it. So read your notes out loud and read it to yourself out loud and hear yourself saying the words. Anything you can do to bring the information back to yourself along different sensor channels, the better luck you have of remembering it. Another big aspect of turning short-term into long-term is restructuring. Right? So rather than memorizing your professor's slide decks and writing them all out, can you rewrite the core concepts in a different way? Right? In that way, you're forgetting all of the incidental details, right? The bold and the light gray bar at the top of the slide. You're actively forcing out all the stuff that's irrelevant and only keeping the stuff that's relevant by restructuring the information. Okay. I'm sure, again, you all have your own ideas about how to turn working memory into long-term memory. We've already talked about recall versus recognition, right? It's easier to recognize something on the screen than it is to be presented with a blank screen and try and remember what the command on Linux is for listing all files in chronological order. So if that's true, why haven't WIMPs or graphical user interfaces completely replaced command line operating systems?
Just because one has more features than the other, I assume, because to make a UI where you can do literally all the command line, I guess it would be.
Well, in Linux, you can do in any of the three major operating systems, you can do more or less all the same thing. It might take you a little bit longer in a GUI. Yep.
Shipping boxes with graphics is a lot more expensive than just shipping boxes with CPUs.
Could be, right? So a stripped down machine that just has a command line prompt, maybe there's a financial reason.
I mean, like if you're using Linux, which is all command line based, like provided you know, like generally, okay, like what you usually use the computer for, it's a lot easier to do those things quicker.
It's a lot easier to do those things quicker. Why?
I mean, I'm not a Linux user.
Okay.
So I don't really
So
know.
we set a Linux user down next to a Windows user. We give them the same functionality. The Linux user, assuming they know the commands, is probably going to finish quicker.
Would it just be because you're, on one hand, you're just typing commands and hitting enter, the other one, you're actually mousing through several.
Could be, right? So it might
links.
take actually longer to mouse over something and click on it than it does to actually type it. That might be part of it. The other drawback of, the drawback of relying on recognition rather than recall is you have to put things on the screen for the user to recognize, right? The million-dollar question in HCI is, what do you put on the screen, right? If you put too much detail on the screen, then it's going to take the user a while to visually search for what they're looking for. They're going to have to scan over the 12 icons until they recognize the one that they know affords the functionality that they want, right? So maybe we try and hide most of the detail, and we try and figure out what is it that the user is trying to do and give them a few options for them to recognize the one that they actually want. But that's tricky because now you need to build in a little bit of intelligence to your interface where it has to infer what the user is trying to do. And this is always dangerous, right? The Microsoft paperclip appears and taps on the screen and says, hey, I think you're trying to do this. Here are 3 possible ways that you might do this. The paperclip and whatever its modern successors are usually wrong, right? It's a hard thing to do. So we can go the extreme route and just have an empty command line box, and we assume that we're going to rely on recall, that the user is willing to memorize all the commands, or try and figure out what to present on the screen to help the user recognize the commands that will get them to their goal. So we're always playing this balancing act between recall and recognition. Okay. Let's talk about attention now. This one has been talked about for a long time in psychology. Again, we don't really know how this one works. There have been a number of models that have been proposed by psychologists over the years. The first one, which is the one that's most obvious and the one that feels most intuitive, is the single channel model. I'm a lighthouse and I have a beam of light, which is my attention, and I can project it to different parts of my external world, and whatever falls within that light cone, that's what I attend to. That one seems a little bit overly simplistic, right? So that was eventually replaced by the allocation model, which is the idea that attention is a finite resource that you have, and you can choose to allocate more or less of it as you see fit. I'm hoping that you're allocating most of your attention to my voice or the slides or your notes as we go. But you're probably also partially aware of how much time is left in this class, whether your cell phone buzzes and there's a message for you. In the background, you're probably also at a lower level, perhaps, attending to other things. And again, you might switch your primary focus of attention based on what's going on in the background, right? Okay. Again, this implies that attention is a quantifiable metric. No neuroscientist has figured out how to measure attention in the brain. We can measure electrical activity, blood flow, oxygenation, not so much attention, but it definitely feels like something that has a finite amount, right? You're probably going to go and study tonight, and your attention is going to run out at some point. Okay. Then there's the controlled and automatic side of attention. So again, this idea of fast and slow thinking. So hopefully you're exerting some conscious attention to stay focused on the flow of this lecture, but there might be other things that go on that automatically steal your attention away from what's going on at the front of the class. And those things are usually fast and relatively cheap, like muscle memory. So here's an example of this, and I'm going to have to switch to presentation mode for this to work. Okay, so as we talk through this slide, if you were all wearing gaze trackers, your eyes would periodically saccade where? To the changing image, right? I chose this one particularly because it stays still for a while, which gives you just enough time to attend back to the center of the slide, and then something changes and your eyes get drawn back. All right, force yourself not to look at that image anymore and see how well you do. I don't assume you'll be able to do this. It's very difficult to do, right? So let me switch back out of presentation mode. So internally, hopefully you choose to attend to the bullet points in the center of the slide. You're making a conscious choice inside to attend to the material, but things can happen outside that you don't have much control over, right? So if anyone at the moment is watching a funny YouTube video and you're sitting behind them, your eyes are going to be pulled to their screen, right? It's hard not to do so. Very difficult. Okay, so knowing that those aspects of attention, think carefully about what you draw to the screen, right? So if you have a timer in the top right of your interface for your system, and it's switching every second, your user's eyes are probably going to be pulled away to that timer, and they're not going to see that they failed to gesture correctly or they succeeded at gesturing correctly. Pay attention or be able to make predictions about where the user is attending, and make sure you choose your visualizations and animations carefully to help the user focus their attention on what you want them to focus their attention on. We talked about visual consistency quite a few times in this course. One of the nice things about visual consistency is if you do want to draw your user's attention to something, you don't need to switch the stimuli very much, right? So everything is in black here. I just need to paint some of the letters gray to get you to focus on that piece. If I don't have anything that's visually consistent, I'm going to have to work a lot harder to get you to attend to the thing I want you to attend to. Right? So all these aspects of attention, they're really important when you start to design your interface. Okay, now we're going to switch to perception. We're going to play a perception game this time. I'm going to flash up a field of ease, the letter ease, and I want you to find the letter F in the field of ease. I promise you there is an F in there. And I want you to just sort of think about how many seconds it takes you to find the F. Ready? Here we go. Everybody found the F? Okay. We're going to play the same game again. I'm going to show you another field of ease. And again, I promise you there is an F hidden inside it. I want you to figure out how many seconds it takes you to find the F. You ready? Ready, set, go. I think there's an F in there.
Is there?
It's a trick question.
Oh.
My fault. My fault.
You all fail.
You all fail, that's right. Okay, F for fail. Okay, as you can probably figure out from these two little games here, I tried to make it hard on you. That was not supposed to be part of it. What is it that makes this particularly hard? Uppercase E and uppercase F look similar. That makes it hard. What else makes this hard?
Clumped together. And also, it's not naturally how you read. In general, like in a column like that.
Well, this one is a little bit more how you naturally read, right?
I was just going to say, unlike the image, it doesn't move, so you have to scan each individual thing.
Absolutely, right? So I'm not making this easy on you. I could have flashed the F and you would have found it instantaneously, right? So you had to actively work for this one, right? You were actively perceiving, with the exception of this one, at least on the previous slide, the F actually fell on your eyes in the form of photons. You probably didn't see it until you scanned. How did you scan? How did you scan for this one?
I just looked at the bottoms because E's, they actually have a bottom, so the F would have a gap in the space between.
Okay, you know the difference between uppercase E's and F's, so you know where in the character to look for it. That's good, right? You're using your mental model to help here.
I just went from just like reading, so I just started top left and just went across the bottom, went down clear up to the bottom of that.
And why did you do that? I didn't give you any instructions about how to scan.
Just experience.
Just experience, right? This one feels comfortable, right? You start in the top left and you start reading, which is why I put the F in the last row, right? If the F had been up here, you would have found it instantaneously. What about this one? Did you read starting from the top left? How did you scan this one?
Just went like down every row,
And-
starting from the middle, and I picked the direction to go.
So why did most of you probably scan vertically? Why?
Because they're stacked vertically.
Because they're stacked vertically, right? So the way I chose to present this data for you influenced the way that you actively scanned this field, right? So again, most of us native English speakers have a natural inclination to scan left to right along the top column and then the next and the next, but we can break that and force our users to scan differently. So as you're starting to add visual detail to your interface in the weeks to come, think about that, right? When your interface flashes up, how is the user going to scan it? If the instructions or the visual instructions about what they're supposed to be doing are in the bottom right, it's going to take them a while to get there, right? If the visualization changes, where do you want them to look to know what they're supposed to be doing next? You can influence them, and you can influence them in a way that makes it easier for them to do whatever it is you want them to do, or it makes it harder for them to do it, right? Here I tried to make it difficult for you on purpose. Okay, that's perception. Again, perception is an active rather than a passive process, and how we lay out the screen influences it. This is an HCI test that was done a few years back where they created some web pages and had users actually wear eye tracking so they could see where the users were looking. Let's play the usual visual metaphor game here. What do you think the circles mean? Where they looked, and the lines mean not their direction.
Like where their eyes went.
Where their eyes moved, right? So the lines represent saccades. They looked here, and then they moved their eyes there. What's the size of the circle represent? How long they spent there, right? Okay. What would you guess is the native tongue of this user? What this picture doesn't show you is sequence, right? So you can't see that they started here and then went here. Where did they spend most of their time? On the pictures, and on the pictures near the captions. So they were probably looking at the picture and reading the captions. Then what? Maybe kind of difficult to see from this picture, but they spent most of their time on the top left here, and then they tended to spend slightly less time here, then here, then here, and they actually kind of went and did the Z pattern. So this was probably someone from the Western culture where they're reading this like a text. If you do this with a non-native English speaker, a native Hebrew speaker, or a native Mandarin speaker, you would get a different saccade of the same page. That person might recognize that this is an English language web page and may scan differently, but you can get at some of these patterns about how people actively perceive. Okay, we got 5 minutes left, and we made it through lecture 12. I apologize, I didn't put up lecture 13 until just this morning, so we'll come back to these slides on Wednesday, but let's get started. So in lecture 13, we're going to continue our discussion about perception, but we're going to focus on a particular school of thought that grew up around perception, and these were the Gestaltists, and they were a particular group of psychologists who had particular theories about how we perceive. One of the nice things about the Gestalt approach to perception is they came up with a bunch of these rules that, again, probably don't exist in the brain, but seem to capture some of the interesting aspects of perception. For those of you that don't speak German, Gestalt means whole is other than the sum of its parts. So onto your eyes continuously are following photons, and you are finding patterns that don't exist in any individual photons, right? You're drawing out a pattern which is more than the sum of the photons that are falling on your retina. One of the first and most important laws of the Gestalt approach to perception is reification. And reification means to make something real. So we often see things that seem real in things that we know are not actually there. What do you see in these four optical illusions. What do you see in the one top left? Triangle, right? There's actually 3 Pac-Mans. There's no triangle there. But your brain tells you there is a real triangle there. It is reifying the triangle in this case. What about B?
Rectangle.
You see a rectangle. Some people see a pole with a snake wrapped around it. Depends, right? There's something there. There's actually only 2 commas, right? But your brain reifies the absence to see a rectangle or a pole or what have you. How about C?
3D ball with spikes.
A 3D ball with spikes. Again, there's no ball there, but there seems to be a sphere there. The spikes are drawn. The sphere is not. What about the 4th one?
Champ.
You see, everyone sees champ, right? Obviously. There's no actual champ there, but you see one long line segment, right? We see faces in clouds. You see patterns and things that aren't actually there. Depending on how you organize things, it's relatively easy for your user's brain to be convinced that there's something there without having to actually paint it to the screen. Okay, so we know that perception is active. You move and you expect to see something when your eyes move. It is also constructive, right? Your brain is taking all of these disparate visual patterns and stitching them together into a whole. The AI revolution that we're in the middle of is because of deep learning, and deep learners do this. And it took 30 years for us to figure out how to create deep learners. They see local patterns at the local level, and they know that if they see this here, and then this here, and then this here, a deep learner would predict at the top level of its hierarchy triangle, even though there is no triangle in this picture. Okay, so perception is active, it's constructive. Beyond that, there's a lot of disagreement in the psychological literature about how perception actually works. Richard Gregory was the head of one school of thought that said, we're always looking for consistencies. So the flood of photons that are falling on your eyes are always different. The pattern is never, ever the same. You're awashed in a sea of chaotic signals, but you tend to see constant things. You see this guy at the front of the room three times a week, right? On the other hand, J.J. Gibson headed up a school of thought that said what we tend to attend to is changes in our world, right? When we had that animated GIF, you couldn't help paying attention to it. So do we tend to focus or perceive constancies more than differences, or vice versa? I think we're out of time, so we'll come back to this on Wednesday. Okay, you have a quiz due tonight and deliverable 8 due on Wednesday night. Have a good rest of your day.